Not yet. Okay.
Okay, so
Oh, wait a
recording
minute.
is on,
Wait,
right?
wait a
Okay.
minute. Yes. Okay, so let's proceed to the next talk. Our next speaker is Leonid Chekhov with a talk, Integrable Structures on Directed Networks. Please.
Thank you so much for this opportunity to present this talk in honor of my dear friend Andrusha Pogrebkov. And I will, so for most of you, it's the end of a long day. For me, it's a beginning. So, well, everyone is a little tired, maybe because of different reasons. So I will try to make it as simple as possible. So that's what my intention. And today I want to describe some structures that actually appear from geometry. So that's why I want to start with this first part, describing what were geometrical origins of the corresponding structures that eventually led to the appearance of familiar probably to the audience structures appearing in integrable equations and like R matrices and even affine structures, affine Lie-Poisson equations, and quantum loop algebras, and it's all related somehow to the notion of planar networks that and cluster variables that actually we interpret, well, we'll see, as Darboux coordinates. So just to mention that everything that I will be talking about today will have actually some quantum counterparts. And my talk is based on several recent papers with Misha Shapiro and also our exchange student from China, Huang Shibo, and of course on many my previous joint papers with Marta Mazok and Volodya Rubtsov, and some of these nice people are here in the audience, so it's my pleasure. Okay, so let's start. And I will start with some history. Coming back about 20 years ago, so the history is related to what we call the groupoid of upper triangular matrices. And well, consider indeed just upper triangular matrices, actually nilpotent, so with units on the diagonal. And we interpret these matrices as matrices of some bilinear forms in some linear n-dimensional linear space. And we can transform this basis of this form using another matrix B. And apparently the matrix of the form transforms not as in just using this transformation. So we have not standard adjoint action, but the action with transposed matrix B. And it was interesting, actually, from the mathematical point of view, to consider some admissible pairs of these matrices B and A, such that this transformation preserves actually this upper triangular form of the matrix A. It just happens that these pairs admit a standard symplectic structure due to Karashev and Weinstein, compatible with this groupoid with the groupoid composition law. But what is actually will be more interesting for myself today is that this structure actually induces the Poisson quantum or boson or quantum, depending. So I just present them on the same slide using different colors. On this set of matrices A. And it's immediately appeared that the structure that arise, the corresponding Poisson relations or the corresponding quantum relations, they are known. They are known for some time, and they appear in many different cases. They appear in monodromies of Fuchsian systems on Riemann surfaces. And from geometrical point of view, they appear as a Goldman brackets, in semi-classical case, as a Goldman bracket in on the case of on the set of geodesic functions on some Riemann surface. So just to mention that indeed these algebraic equations are very much known, very much famous, and actually they were known also long before on the integrable side, because well, if we organize now these items in the quantum matrix, so quantization here means that all upper triangular elements are considered self-adjoint operators, enjoying the quadratic linear algebraic relations on the previous slide. And by some reason, we have to also amend the unit elements on the diagonal by these Q factors. If we do it this way, then it happens that this matrix A satisfy quantum algebra known as a reflection equation in integrable theory. This trigonometric R matrix, which I will describe later in my talk, well, explicitly, but just, well, again, so I'm happy then probably in this audience, I should not explain what R matrix is and what are these notations of spaces 1 and 2. Of course, it's a notations in the tensor product of classical spaces where elements of this A lives in the same quantum space. So again, if I come back to geometrical origin, this equation, reflection equation, or this matrix A that I have here, actually can be identified with special finite subsets of geodesic functions. So we can identify the entries of this matrix with double hyperbolic cosines of lengths of actual geodesics on the Riemann surface. And since Goldman, it's known that these combinations, these hyperbolic cosines, they are, so to speak, good algebraic objects because they are simultaneously also traces of monodromy matrices in some Fuchsian systems. What was known again for many years is that if we make this identification, then we can parameterize the corresponding quantities in corners of quantum Teichmüller spaces. What was unsatisfactory, however, is that in this story we can parameterize it very well for lower n's like n equals 3, 4, and partially 5, but for higher size of this matrix A, basically we cannot parameterize in terms of this quantum Teichmüller spaces, these coordinates, we cannot parameterize the higher dimensional Poisson leaves of the corresponding Poisson structures or quantum structures. And again, there was a problem So that's, you see that here in the bottom part of this slide, I indicate that we have mismatch between dimensions. So we start with the same numbers, but then they, of course, they diverge drastically. And there was a problem of finding the corresponding Darboux coordinate representation for just general Poisson leaf of the corresponding reflection equation. So this was one motivation. Another motivation actually also came from the representation of quantum break group transformations for the same, in the same upper triangular matrices. And again, we know that there was this quantum break group action. And so we addressed with Misch-Shapiro the problem of, actually two problems simultaneously: finding a cluster variable realization of a general symplectic leaf of this matrix A, and cluster mutation realization of break group transformation. And this was done like in our paper of 2020. I will briefly describe it now. But before I come to it, I come to this description, I have to slightly change decorations and come to the next and probably main construction that I want to present today, and namely this directed or direct planar networks. There is just one example, also very important, but just one example of these planar networks presented here. So it's related to the Borel subgroup of SL6. And what we have here? So we have here, you see, the graph and dual to it. So I have my main graph just have a solid and dashed lines, and vertices of this graph, like at all vertices, we have what we call a cluster variables, but in physical, from the physical point of view, they are just canonical, actually exponentiated canonical coordinates, because we have these blue arrows, and blue arrows actually encode commutation relations between these variables, and here we have it. So we have, if two vertices are joined by the solid arrow, then we have this commutation relation, as you see here. And if they are joined by the dashed arrow, they have half of this commutation relation. And now what we have, we now consider actually passes in the dual graph that is indicated by double arrows. So if I consider a pass in this graph, like going from one, so from the source number 3, say to the sink 5'. So it's some. So what we do with this pass, we just take the product of all variables that lie to the right from this pass. Of course, it's optional. Well, it's just convention, but that's convention that will stick in this talk. So we just take this product and we make the while order product of this. So basically, well, again, hopefully I shouldn't explain what while order means, but at least this means that this element itself is self-adjoint, because we also have, we also assume that we have a C-star structure such that all this, oops, it's very insistent, sorry. all these Z variables are actually self-adjoint or exponents of some self-adjoint operators. So we just have this product, and then next step. So this next step is just to. So this I have this description how we can actually make how we can construct this network or any other network out of elementary blocks. So elementary blocks are related to white and black vertices in the dual graph, and around each white vertex I have this structure of dashed arrows. So they are clockwise oriented, and around each black vertex they are counterclockwise oriented. And actually I collect my bigger cluster variables, so Z variables, out of these wedges. So like I did here, so I have, for instance, if I have the hexagon, and I have this variable Z alpha at the center of this hexagon, it is actually collected out of 6 wedge variables, and all wedge variables in separated triangles, they commute. So the only non-trivial commutation relations between them are inside the small triangles, and basically these produce the corresponding bigger Poisson or quantum structure that I indicated by the blue arrows on the previous slide. And it happens that, for instance, if I have 2 vertices Z, so this that I indicated in red, separated by the edge between stretch between white and black vertex, the direction of double arrow is irrelevant. Then we have this commutation relation that is encoded in this blue arrow. If I have on the boundary, so on the boundary, remember I still have these dashed arrows, and then again, so it's satisfied. So if it's source or sink here in this right part, or source of sink in this left part, then depending on the color of this vertex, I have the corresponding Poisson and quantum relations between the corresponding cluster variables. And finally, if I have 2 black or 2 white vertices, also I don't have them in Fogg-Goncharov graph, but basically we are able to consider any graph, any planar graph, then the corresponding variables commute. Okay, next part and most important is that now I want just to construct transport elements. Now they are enumerated just by sources and sinks. And it's easy, I just consider sum over all passes that join this source to that sink. And for each pass, remember, I have to just to take a linear sum of the corresponding weights of these passes. Again, what to mention? It's actually, this formula is very general. So it works for any planar directed network. For example, I can assume that we have some loops in this network. So then this sum becomes infinite, and the corresponding expressions become rational. And I have to introduce, then if we have loops, I have to introduce the factor of self-intersections. But besides that, everything is very much explicit. And what is probably sort of amazing is that for any this planar directed network, the corresponding quantum algebras of these transport elements appear to be very simple in a sense, and appear, you see in the form, it's almost exactly the quantum algebra that we have for elements of reflection equation. It's still not reflection equation. On the next slide, we'll see how it's related to integrable systems. But just to mention that again, it's closed first, right? You see that actually it's always closed for any planar network, and it's quadratic in terms of the corresponding elements of this transport matrix. It's not also to mention, it's not out of blue, because semi-classical version of these relations were obtained by Mishas, Geffen and Shapiro, and Alec Weinstein, sorry, in more than 10 years ago. But we were able with Misha to produce some quantum version quite recently. And again, so these matrices, these algebras, they appear in systems related to SLK on Teichmüller spaces or outside Teichmüller spaces. And again, so there are many authors who made it, and I can mention also Misha and Sasha Shapiros, Gus Schrader, and Marta and Volodya Rubtsov, and myself. So again, if we come to this original example, the original example of network in the Fogg-Goncharov quiver for triangular matrix, for triangular quiver. And we just need to define some small thing is that we consider not transport matrices themselves, but some transformation of them with Q is some diagonal matrix with Q factors here, and S is anti-diagonal matrix. It's necessary from the point of view, this multiplication in semi-classical form is necessary from the point of view of forms on corresponding flag varieties. So it was in paper, still in the first paper by Volodya Fogg and Sasha Goncharov. But if we now consider this system, and we consider the above relations between elements, between entries of these matrices, it's interesting that for this triangular system, again, so let me just show for a second the system that I'm talking about, because I have sources on one side and I have two sets of things, and I define this transport matrix correspondingly have a block quadratic form, and with each square in this matrix I associate the corresponding block. So this M1 and M2 are actually two blocks in the corresponding transport matrix.
Leonid, I'm sorry, you have 5 minutes.
Oh, that's fine. Yes.
Okay.
Very good. So, and you see that they satisfy the R matrix relations, where R matrix is a quantum R matrix, trigonometric R matrix, again, appeared still in, I think, in the very first paper by Kulish and Sklanin. We also have the quantum groupoid condition, which will not play much role in my today's talk, but of course it's important from the point of view of consistency for SLN monodromy systems. What will, however, play the role is the next statement that now if we take just this matrix product of these two matrices in this particular graph, then the corresponding matrix A actually enjoys the reflection equation. So we can parameterize, therefore, all higher dimensional Poisson leaves of the corresponding yes reflection equation, and simultaneously what we also obtain, it's actually holds true for any this system with these two matrices M1 and M2, because again recall that the algebra does not depend on the particular network. So the only thing that is relevant is the distribution of sources and sinks. So we can actually do the same for literally any network with n sources and 2n sinks if they are separated. But of course, for the reason of constructing representations, possibly in this situation, the Fogg-Goncharov quiver is the most important one. And now, in my last 2-3 minutes, I will now come to generalization, how we can construct realizations of affine Poisson equations in the same system. If I have any planar directed network, okay. So now let's consider a network with n1 plus m sources and 2 plus m sinks, where n1, n2, and m are arbitrary. And I consider, so now this transport matrix has a block form. And in this block form, I consider n2 times matrices of size n2 times n1 tk, which are defined by definition in this way, where the most important for me is this square matrix m12 of m by m. So it's square matrix, and I indicated this matrices by these fat arrows in this picture. So what is interesting, that this m can be arbitrary. For instance, we fix n2 and n1 possibly to be the same number, but it's also not important. But then we can consider m to be arbitrarily big. So we have plenty of Darboux corners. So we can consider a embedding of finite dimensional leaves into infinite dimensional affine Poisson algebra, but these leaves can have enormous dimensions, finite but enormous. Basically, we can make arbitrary number of these tk to be algebraically independent. And for any such system, we have the same now Poisson equation with a trigonometric R matrix with a spectral parameter. So in the last slide, so this is one example that we have, possibly the most important one. So we take n1 sources and 2 sinks, and we just take other m, well, can be again arbitrary. For instance, in this case, it will be 2 by 2 affine system. And well, so the last is that we can not only produce the Poisson, but we can make, using this standard structure, using this standard relations that I present here. Also, it's due to Drinfeld and Reshetikhin. So out of this quantum loop algebra, for which we have two sets, T plus and T minus, we can construct the quantum affine reflection equation. And what are these two sets in my case? Again, this is just my last slide. So T plus is the same as above, and T minus, to get T minus, I have to assume that I am able to invert this matrix M12. So it's the only assumption that I have to make, and having it, I can claim that if I have these two half-infinite sets, they will satisfy at the end of the day the quantum loop algebra, and we can present the quantum affine realizations of Poisson leaves or quantum leaves of quantum affine reflection equation. Okay, so just about the perspective, just let me, of course, the most important and probably most interesting is how we can construct representations of these algebras and how they are related to the known representations, like in beta ansatz form or other forms. But the most important, my last slide, of course. Happy birthday.
Спасибо. Thanks a lot.
If someone is interested, what is that? If you take it.
Everybody is in.
It's good to know.
On a Russian keyboard. I saw it so many times, so it's my new signature.
Thank you. So
And
please,
just
questions.
let you draw your attention that we'll have a 8th Moscato conference next June.
Okay, so
Yes.
please, questions.
Okay.
Comments? Well, thank you very much once more.
Okay, thank you.